A look at the new model perturber I've implemented. So um, this one actually goes beyond the model edges, so we get a truly uniform distribution. So instead of just going from nx, or on the interval of nx, I'm actually going on the interval of 3 times nx and minusing 1, so we're centered. Everything else is the same, except I've added this additional criteria that it has to be within the model. So Ix from has to be less than the easternmost of the model. Ix2 has to be greater than the westernmost part of the model, etc. So this just makes sure that the cube is actually going to be in the model. I've also added a while statement, so this guarantees that this is going to return an acceptable model. When this is activated, it's going to exit the while loop. Otherwise, I noticed that this one the models were converging much slower than they were before, and that's because it was getting hung up. So now I can get through. I'm just going to quickly show how much more uniform these models look. So this is 2 runs. These are the same thing, so we can just talk about the one on the top. So what we're looking for is that the corners are being sampled better than last time. Remember last time we had this nice red kind of circular shape in the center. We had blue in the corners. This time through, you see that the blue regions are more randomly distributed. The corners seem to be getting hit even more so than some of the other regions. This corner is not being hit, so I mean it's random, but if we look at this one right here, this edge is getting hit very well. This corner is getting hit very well. So I believe I've solved the issue with the distribution in our model perturber. So I'm going to go ahead and stop this. It seems to be proven to be effective. What we're going to look at now is the results of one of my stochastic modeling runs. So what this is doing is it's doing a hill climber algorithm 300 or 100 times. Each hill climber has an iteration max of 300. I just sort of empirically noticed that that's about when it kind of stops converging further. This one in particular is way out of bounds, considering that the average error from all the models, 100 runs, was 3 to 4 orders of magnitude less in error. So after 100 runs, we wind up with sort of a stochastic density model. We're not really getting good control on the vertical, which is expected. However, we are getting really good control on the vertical, the position of the horizontal position of the contact, which is, that's what we wanted gravity to bring to the joint optimization. So I feel like it's achieving that goal pretty well. This is just a stochastic kind of fun model, not really too important, but it does seem to show that we can at least capture that that the position of the horizontal contact is much less non-unique than the vertical position, and that's where the seismic will come in. So I just wanted to give you another update. Have a nice day.